welcome to math analysis. So today we talk about this thing which is called the Dirac data function. So this Dirac data function is a very important function in mathematics, and it is used everywhere. Especially it is used in physics, especially in the in physics. Physicists, they use some functions, so they have to use this to identify certain function in certain domain. So let's think about this and let's see how it is done. So first things first, that what is the history of this? Basically what happens that Paul Dirac, he was a great physicist. So it is not actually a contribution of mathematician rather than a physicist. So Paul Dirac was indeed a great physicist. So he discovered this function, and when he discovered this function was like, so-called trending everywhere, and it is used everywhere because it has so many good properties, so that you can apply this function in so many parts of mathematical formulation and mathematical proof. So let's see what happens. So let's think about R, or any field. So I'm here talking about R because that is the simplest ever field what you can get. So let's talk about R. So of course R is the set of real numbers. So let's think about a set A. Okay, so A subset R, common point. So A is a subset of R. So now what is direct delta function? So you see that that is the whole R, and there is a set A, that is set A. Okay, so this direct delta function works in certain way that over R, if you try to define a function over R, so it will only concentrate on A, not on R. So that's how the function works. So if imagine there is a function, but you want to like cut down the function, or you try to extract the function from a certain domain or from a certain set. So this function is pretty helpful for you. So the function defined over this, in A the function is A, and except A means A complement, that should be 0. Okay, so now you got the clear point of view of this function, and this function is defined over defined like this. So okay, I'm talking about only delta. So delta x, that is a symbol delta, that is the symbol of delta. So delta x is defined by that way. So it is 1 when x belongs to A, and it is 0 when x does not belong to A. Got my point? So when the point x in A, that is 1, but when the point not in A means A complement or R minus A, the function is basically 0. So now you see how it happens. Okay, so only on A the function will try to concentrate it on A, and except A the function is totally 0. So that's what the direct delta function is. That is very simple indeed, but in theoretical physics actually it is used so many times. It is used like randomly. So graphically, if I represent the function over R, let's say this is R. All right, so this is R. Now we define the function in this way. So let's see this. So let's think about a subset of R. Let's say 0 1 closed interval. So that is 0, that is 1. So if I want to take this A as closed interval 0 1, and if I want to define direct delta function on R, of course the function maps from R to R. Okay, that delta maps from R to R, and so so that will be 1. Okay, like this, and except every point that will be 0, like this. Okay, so that is closed one, the height is 1, and except at other point the function will be 1, 0, like this. So that is the general idea of this function. Okay, that is what is called the direct delta function. Thanks for watching.